Okay, so what goes wrong with our naive speech perception model where acoustic features roll in, you identify them, you associate them with linguistic features, and thereby perceive speech? Well, here's some things that we looked at last time. First of all, acoustic cues to various sounds or various features are not actually neatly separated in time. They tend to occur at the same time, and we refer to that as co-articulation, or as the acoustic effects of co-articulation, which is maybe more properly an articulatory concept. Shown here are an acoustic recording of the sequence peace plots as recorded by an English speaker, and then a bunch of X-ray pellet tracings. So this was an early way of gathering articulatory data in phonetics. This is again the Haskins labs in the probably 1970s for this data. What they have here is a bunch of lead pellets that you put in various places in people's vocal tracts, and it allows you, using an X-ray machine, to then track where those pellets are moving over time. And so here we're tracing the tongue blade, that's the area just behind the tongue tip, as to how high or low it is. Here we're tracing the sort of middle of the tongue, something like the dorsum, again, how high or low the dorsum is. This is the tongue, really the back of the dorsum, or maybe even the root. I guess you probably can't get an X-ray pellet really far into the pharynx, but it's a bunch of tongue positions. Here's the lower lip. Is it high and joined up with the upper lip, or is it low and leaving an opening? And here's the jaw. This one's probably placed externally, right? So we're tracking how high or low the jaw is. You can see it's pretty high for consonants. It's a little bit lower for a high vowel, but a lot lower for a low vowel. And this is a record over time of how your articulators are moving when you're producing this utterance, peace plots. Right? So what do we see going on here? Well, right at the beginning, here are some things we can see. You are bring your lower lip up to your upper lip, right, and producing this closure that's for a bilabial stop. And by the time you release that, you're already moving your tongue blade and maybe the area behind your tongue blade towards the target for this E vowel. Right? So the E vowel is going to be this one. Actually, I'm confused here. It looks like there's 3 syllables in this recording. What is going on here? This is probably P splots. Yeah, I'm not sure how this acoustic waveform actually matches up with the transcription they've given here, but let's assume that it does somehow. Oh, I see. Okay, so the P sound actually starts here, right? My bad. This is the resting position before you say anything. This might be something like P splots, right? So here, you're moving your lower lip up towards your upper lip to create a closure, and at the exact same time, you're moving your tongue body and your jaw down to the target for this E vowel, and that's not happening neatly after this P sound. It's happening at exactly the same time. Right? And more generally, this is what you find. So you get your jaw down in this configuration for the E vowel, and by the time you do that, your tongue tip is already moving towards this S constriction at the alveolar ridge. This is happening roughly at the same time. These are overlapping in time, and that means if you pick any particular point in this acoustic waveform, you're not just going to have one of these segments happening. You're going to have a whole bunch of different articulatory movements associated with different sounds going on at the same time, all being reflected at the same time in the acoustic record. That's what co-articulation is. Because of that, means the acoustic cues to any given feature can also be very different in some contexts than they are in other contexts. Excuse me. This is the problem we referred to last time as the lack of acoustic invariance. And again, if we look here, presumably, right, the sound of a puh being a puh in this context, right, where you have this lip closure, but there's all these other tongue things going on behind it, it's going to sound a little bit different than it does over in this context where there's different tongue things going on behind it. So again, there's going to be some acoustic differences between this puh sound and this puh sound. That's the lack of acoustic invariance, and some of it at least is due to co-articulation. And it also means that some acoustic things that are good cues to some linguistic feature X, like labial, in one context, might be a better indicator of some other feature, like say dorsal, if you put it in another context, right? We saw this as well with the ambiguous stop burst artificial stimuli last time. Right? So this problem of co-articulation really makes our model of how we're going to pick up features over time significantly more complicated. It means you're not just necessarily going to be able to look at, this particular stretch of speech and know exactly what kind of a speech sound it is, because it might depend on what's coming next. And the particular features of this vowel ah might depend on what came before and what comes after, right? You can't necessarily just look in here and go, oh, F1 is 800 hertz plus low, right? It's not that straightforward. There are several other problems with this sort of naive acoustic theory of speech perception, and these relate to the other sort of perceptual, interesting, fun things that I showed you at the end of last class. So for one thing, there's categorical perception, which shows that, if your ear and your mind are, straightforward acoustic detectors, there's some unexplained properties of those detectors that don't seem to follow from that. Namely, there's this categorical perception phenomenon. And here I illustrated this with the difference between a labial and coronal stop, but this is true equally well for voiced and voiceless, for voiceless and voiceless aspirated stops, for any other place of articulation. For most consonantal sounds, you get this kind of categorical perception phenomenon. And what that refers to in its sort of quickest form is this discrimination curve. This is the dashed line here, where guessing and performing at chance, like random chance, would be 50%, right? Because the question is, are these two things the same or are they different? Right? And the claim here is that discrimination across a category boundary, like up here where you might have one stimulus at step 4 and one at step 5, that discrimination performance is always going to be better than discrimination within a category, where you have, for instance, a 6 and a 7 that both count as duh. Right? It's going to be harder to discriminate them than an equally acoustically separated pair at 4 and 5, where one counts as a buh and one counts as a duh. Now, in order to figure out where that category boundary is, you also need this identification task, which I talked about last time. But the categorical perception part of it, once you've located the category boundary, the claim is that discrimination across a category boundary is better than discrimination within a category. So that's sort of an issue. That's unexplained if we're just detecting raw acoustic properties. Duplex perception has to do with these high-pitched whistles and beeps and sort of bird tweet things. And I didn't find a pure example of these for you, but I played you that sine wave speech last time, where most of that speech is made up of these kinds of pure tones up in these very high frequency ranges, and it sounds like R2-D2, right? It sounds like a robot beeping and whistling until you put it onto a realistic speech-like bass, and then all of a sudden, the way you perceive these clicks is totally different. In isolation, you perceive them as two different bird tweets or something, but when you put them onto this formant-based framework, you stop hearing the tweeting part, and you just hear da or ga, right? At least in this experiment. Now, interestingly, there's also a version of this duplex perception where they play the tweet part in one ear and the rest of it in the other ear, and here people simultaneously get the tweeting part and the speech part together. This is duplex perception. It's the claim that even the same sound can be treated very differently depending on whether it's processed as speech or as non-speech. So that's, again, if you're just detecting raw acoustic properties, that's going to be very hard to explain. And then there's the Mcgurk effect. I'm not going to make you go through this again. We looked at this in class. And here we noted that at least for some very strongly visual features, like a labial closure in a sound like pa, that what you think of as your auditory perception, that is your speech perception, what you hear, is strongly influenced by what you see. And in that stimulus, we saw a recording, an audio recording of somebody saying pa was mixed with a video recording of them saying ka. And what you usually hear when you're watching the video is something halfway in between, namely it's close to ta. Although as Shahid noted, it's a really funny sounding ta for English anyway. She said it sounded a little bit like the Arabic emphatic consonants. And I think that has to do probably with the extremely long voice onset time, which would be characteristic of those emphatic consonants in Arabic. And also maybe with the mismatch between what you're hearing as a ta and the formants at the onset of the ah vowel, which are going to be lower because it's actually a pa. And that also might create the perception of pharyngealization, which is what those Arabic emphatic consonants have going on. So I'm not sure exactly why it sounds like a pharyngeal consonant, but I think Shahid is right. It kind of does. But in any case, the point is that you don't hear pa and you don't hear ka. You hear something in between because you're blending information from the auditory stream, which is a clear pa, and you can see that when you close your eyes, and the video stream, which is clearly not a pa because there's no lip gesture happening. And you're blending those two sources of information, yet perceiving it as a single unified whole. So again, if you're just listening to acoustic features and sort of listing them as they come in, this is going to be very difficult to explain. The motor theory of speech perception arises from decades of this early research at the Haskins Laboratory, and it's meant as a way of addressing all of these problems that have arisen in studying speech perception over the, let's say, 25 years between 1950 and 1975. So let me again split this out in a separate video. I'll talk a little bit about how speech perception started as a scientific field, how it got here, and what the motor theory is going to have to say about it.